Welcome everyone to one of our first lectures of chapter 4, 4.1, and it's talking about radian and degree measure. So I know we've dealt with a ton with degrees in the past, 45 degrees, 60 degrees, 180 degrees, that's more common. And we've seen a little bit of it last year with radians. That's when we included pi and all that jazz, and we're gonna do the same thing here. But before we can get to our trig functions, we gotta know how to use some of the basics. So first things first is just talking about angles. So listed for you guys are three common variables we're going to be using. So we have alpha, beta, and theta. Theta is probably going to be the most common that we're going to see. And these are just variables for our angles. Typically, x is more of a measurement of distance. So we're getting a little more specific of what variable means what. Now, with our angles, we have a couple things, a couple standard things. For starters, we typically always have this positive x-axis as our initial side. So if that's my starting point and I kind of swing through some angle, it's always going to be starting on that positive x. And we call that the initial side. You swing through, and where you stop, that entire span is your angle. And where it ends, that's our terminal side. Now, kind of my note down right here that we're always starting, it's standard to start on that x-axis. And it's also standard that we swing counterclockwise through this. So counterclockwise, if we start at standard and do counterclockwise angles, that's actually going to be positive angles. And if we start at that standard and actually go in a clockwise manner, that's going to give us negative angles. So a little counterintuitive, it's going to the left ultimately positive and swinging back down negative. Now, based off where we start or end any of our angles, we have something called coterminal angles, which are a special type of angles. And ultimately, these are angles that share the same initial and the same terminal sides. Well, if we can't change that, the only thing we can change is the direction we go. So if I have this initial angle and I swing it through to this terminal side, that's one angle. So a counterpart to that makes it coterminal would be starting initial and swinging in the negative respect. Now we can have actually infinite coterminal angles. I could have done this. I could have done this. I could also do one full revolution and then end right there in the positive direction. Or we could have done that in the negative. We could have kept going, gone one full revolution, and then kept going until we landed on that terminal. Technically, we started at the same initial. We swung through one full rotation and then some, and we still end at that same terminal. So with coterminal sides, we can technically have an infinite amount, and we're either removing them from 2 pi, so we'll see what 2 pi is, or removing them from 360 degrees, or you're kind of adding copies of those rotations. Similarly, if I were to have just this little smaller angle, a coterminal angle, we could do one of two ways. We could go in this negative direction, or we could have gone from the same start, done one full rotation, and then come back to that same terminal side. So when we're doing coterminal sides, we can find a bunch of different copies. It's just a matter of direction that you're going. You're either going to make up that difference of one full revolution, or you're just adding copies of a revolution. Now, for the most part in the past, we've dealt with degrees. So in this class, we haven't taught a ton about degrees, but typically we're more comfortable with degree measure. But we're going to be introducing now radian measure. So quick little definition of a radian. A little reminder, this is when we dealt with pi, so 3 pi, 5 pi, all that jazz. And ultimately a radian is this. If I had some full circle, right? If I have my radii of the circle and I swing through an angle such that this, which is called the arc, once that is equal to 1 radius, we stop. and whatever angle that is the definition of 1 radian. Now, we don't typically use this definition, which is, that would be 1 radian. Over here is 2 radians, 3 radians. We typically are having it in terms of pi. So that we're more comfortable with it in terms of pi, I'm going to run through some common angles in both degrees and in radians for us. And instead of starting at this right here, which you guys have, I'm actually going to start down here and kind of construct the rest from it. So if I were to start here and swing through this angle, we know that that's just 180 degrees. But as far as radians, this is pi radians. So again, that's 1 radian to 3 and some change gets us halfway there. And that's exactly what pi is, right? 3.14. Well, 3.14 of these sections fit in that top half. Well, if this is 180 for halfway, a full rotation, we know is 360 degrees. So if half a rotation through the full circle is pi, and you double it, well, you end up with 2 pi. So we got 2 pi is 1 full rotation. Pi is a half rotation. And now I'm going to kind of work my way backwards. This is really just half of whatever this is, right? So, well, half of 180, we know this. This is that right angle. That's 90 degrees. But then we're just taking this starting point of pi, right? And we're cutting it in half. So this is also in radians, pi over 2. Now we're going to continue that idea. Over here, we took that half circle up top and cut it into 3s. And that's really an angle of 60 degrees. But again, if we cut this half circle, this half rotation into 3s, we just took pi and divided by 3. And we got the last two. Taking that top half, divide it into 4 sections. We know that typically as 45 degrees, but in radians, we took that half and cut it into 4ths. That's our pi over 4. And then lastly over here, we took that top half and cut it into 6 equal sections. We know that as 30 degrees, or if it's taken this half and cut it into 6 sections, pi over 6. So really common that pi over 6, pi over 4, pi over 3, pi over 2, pi and 2 pi are going to be really common radian angles we're going to be working with for the next few chapters. So here's some extreme basics on them. We're going to do a little bit of some examples of dealing with coterminal angles and kind of bouncing back and forth between radians or degrees. So as we look kind of at that first set of problems, our focus is that topic of coterminal angles. And although on your sheet you don't have it, I would get comfortable, if I were you, at being able just to roughly sketch what these angles will look like. It's going to help a ton down the road when we bring in triangles and all that jazz. So the more practice you have with it, I would say the better. So for number 1, we're looking at the degree or radian of 9 pi over 4. And here's how we can interpret that. Again, 2 pi is 1 rotation. Well, 2 pi here, if we had a common denominator, right, would be 8 pi over 4. So that's 1 full rotation. And then we go another 1 pi over 4. So ultimately, this angle is going to be starting on this terminal side, or initial side, like it always should, doing 1 full rotation, and then ending at that roughly pi over 4. Now, this can help us get coterminal angles, but I wouldn't always rely on just that image. We want to be able to do it algebraically as well. So if we are starting at this 9 pi over 4, we can do one of two things. As long as that next angle stays positive, then it's a positive coterminal angle. So we can either add another full rotation, so add 8 pi over 4, or in this case, because we went over 1 full rotation, I'm going to remove 1 full rotation, so remove 2 pi, and that'll give us, well, just that initial pi over 4. So we'll give it a shot. So we get 9 pi over 4. I'm going to remove one full rotation because I got more than one rotation here, but I need a common denominator. So 9 pi over 4 minus 8 pi over 4, and we get pi over 4, which we can kind of see in our little bit of a sketch. Now, here's the reason I decided to subtract 2 pi. You could add 2 pi, totally fine, as long as that final angle is going to be positive, so some rotation of that 2 pi. The reason I did that is because if I were just to subtract 2 pi for the negative 1, it's not quite there, right? It's still a positive pi over 4. So that means I really need to remove 2 full rotations to get it to be something negative. So I could either start right here, again at 9 pi over 4, and subtract 4 pi, so 2 full rotations. Or since I already removed 1 and got to pi over 4, I can use that kind of as my new starting point and then remove 1 more rotation. Again, we need a common denominator. When we change it, 2 pi turns into 8 pi over 4. Well, 1 pi minus 8, we get negative 7 pi over 4. So again, I could remove another 2 pi, and that's another negative coterminal angle. So I can keep doing that over and over and over in the negative or in the positive direction. Sorry, positive or the negative direction, but we're just looking for 1. So number 3, we got something similar. I'm going to give it a quick sketch. We kind of just saw that we had it sketched over there. Pi over 3 is about right there. That was our 60-degree angle. Well, we have 2 things we can do. For 1 positive, we could add another 2 pi to it, and that'll get us 1 rotation into it. So if we add 2 pi, it stays positive. So we'll get to that in a second. And because this angle is less than 2 pi, if we remove just, 1 full rotation, so 1 2 pi, then that'll get us, into something that's more of that negative angle. This ultimately will get us from the initial, going backwards to the terminal side, that'll be this guy. And then over here would be if I started at that terminal and added 1 more full rotation to it. So now just by even doing that, my image is a little bit messed up, right? I have a bunch of stuff layered, so let's make sure we can do it algebraically. So we're adding 2 pi, get a common denominator. Pi over 3 plus 6 pi over 3. We end up with 7 pi over 3. That's a possible positive coterminal angle. We could add another 2 pi and another 2 pi and keep that going. And then for here, for the negative, I'm subtracting 2 pi, again, common denominator. Pi over 3 minus 6 pi over 3. And I could have removed 4 pi or 6 pi or 8 or any multiple that's a full revolution and still get a negative coterminal. I'm just going for the next closest one when I do this. So I get pi minus 6 pi, negative 5 pi over 3. So when you're looking at coterminal angles, it's nice to kind of have a visual. You don't have to. But I do suggest, if you can, at least give it a quick sketch so in your head you can relate, say, pi over 3 to what it looks like as far as an angle, because it's going to help us down the road when we bring in triangles. Well, that's coterminal angles. We have other special angles, and we know these from way back in geo, if not before that. That's complementary angles and supplementary angles. So, reminder, complementary angles, that's dealing with our 90 degrees, or for us, in radians, pi over 2, right? That half rotation, we cut it in half. That's pi over 2. And then supplementary is dealing with that full rotation from 0 to 180 degrees. But for us, as far as radians, that's 1 pi radian. So if we're looking for complementary and supplementary angles, we're really looking for it needs what added to it to get to pi over 2, and what added to it to get to pi. So again, I just want to do quick sketches. Pi over 6, it means we take that top half and divide it into 6 sections, so this should be a smaller angle than we saw over here for pi over 3. As we do, and this pen is dead. So that's our roughly 30-degree angle. That's that pi over 6. So there's a few ways to go about this. Well, one is you could count how many copies of that pi over 6 you need to get to a full pi or pi over 2. But again, we also want to be able to do it just strictly algebraically. So we have pi over 6. And now you want to add what to get to pi over 2? Well, instead of just guessing and checking, we can solve for x, right? So we could actually rewrite this starting with the pi over 2, and we remove what we know to find out that missing chunk right there. So minus pi over 6, just like over here, we need common denominators. So we get 3 pi over 6 minus pi over 6. That's 2 pi over 6. Or simplified, that's a 1, that's a 3, we get pi over 3. And that should make sense, right? Pi over 6 is 30 degrees. Pi over 3 is 60 degrees, and that 30 and 60, or that pi over 6 and pi over 3, better give us that 90-degree angle. Now, similarly for supplemental, we're not subtracting it from pi over 2. We're taking our top half circle, which is pi, and we're subtracting our little segment from there. Again, common denominator. So 6 pi over 6 minus pi over 6. And then from there, we have 6 minus 1, so we get 5 pi over 6. Which again, this one should have been a little easier just from the picture, kind of what we did before. If I have pi over 6, that means I took that top half circle, and I cut it into 6 pieces. Well, if I have one of those 6, how many more to make that whole piece? I need 5 more. Now that brings us to number 4. Again, I want to sketch it. You'll see why. 5 pi over 6, oh, lo and behold, right? We just found 5 pi over 6. That was this missing piece there. So that's almost a full half rotation, except for we leave that 30 degrees. We leave that pi over 6 left over. And we want to find complementary and supplementary. Now take a moment, either from knowing the value or looking at the quick sketch. If I pass that 90-degree mark, what do I add to get 90 if I'm already past it? And the issue is nothing. There's no 2 positive angles that are going to add up to give us either 90 or that pi over 2. So our complementary, because we're past 90, doesn't exist. What a bummer, right? Now for supplementary, it does exist. And we could do this a few different ways. You could look at the graph and go, there's 5 of my 6 pi's, so I have to have that 1 pi over 6 left over. We could look at the problem above, right? That's exactly what we have right here. We just have the opposite case. So we go, oh, then it has to be pi over 6. But worst case scenario, you can always do it algebraically. Oops. So we have pi minus 5 pi over 6 to get this last little segment, that supplementary angle. Common denominator, 6 minus 5, it's a 1, so 1 pi over 6, which was to be expected either from that image or from just that last problem, since those were already opposite angles. So again, coterminal angles, an infinite number of them, either in the positive or negative direction. We typically try to get the closest one from where we're at, so either add or subtract a full rotation. Complementary, supplementary, exact same way we do it before, but now we're just dealing with it primarily in radians. As we're going to see, we're going to kind of ditch degrees and deal mainly with radians. And now the last thing is to be able to do that, which means we need to be able to go from degrees to radians, or worst case, we're in radians, we need to be able to jump back to degrees. And without just going, I have to memorize it, we want to have that process down. So number 5 and 6, we're dealing with degrees first, and we want it to be in terms of radians. Now here's a nice way to remember the ratio and the order it goes. If you start with degrees, you're going to multiply it by pi over 180. Because we know that this ratio is true, right? 1/2 rotation is 180 degrees, so pi is equivalent to 180. Now, to know if you do it pi over 180 or 180 over pi, here's the trick. If we were trying to write it in terms of radians, we want to introduce pi, so it goes up top. And as we'll see kind of on that last or the next page for it, if we're trying to go from radians to degrees, we want to remove pi. So pi will actually go on the bottom so that it cancels out. So now we got that process. Now we just multiply. We got 60 pi over 180. We can simplify that. 60 goes into 180 3 times, so this is just pi over 3. We already saw that kind of when we did those kind of few key angles. So if you know already which is which, and you can jump straight to it, totally do it. Things like 320 might be a little bit weird for us, but we have this method now. We can just multiply by pi over 180. Well, that gives us 320 pi over 180. 2 is going to go into both of them. More than 2 will get 20. So we'll get 16 pi up top over 9. So again, when we go from degree to radian, you're either going to multiply by pi over 180, or as we see, 180 over pi. If we go to radian, pi is up top, we're bringing it into the problem. And if we're going from radian to degree, we're going to flip that, as you'll see on that next page. We will have the opposite, that reciprocal. And here's why. We're trying to remove the radians, remove the pi from that. And when we flip that, those pi's will always cancel. Well, when we finish multiplying this across, we get 180 divided by 6, which is just 30 degrees. Which again, we saw from those key examples, that pi over 6, that half circle up top cut into 6 little chunks was 30 degrees. Now lastly, number 8. Again, in time we'll probably have these memorized, but for now, how do we do it? We want to remove that pi. So we're going to introduce the 180, introduce the degrees side, and when we divide by pi, it's going to cause us to remove that radian side. Well, now we can multiply this across. We have that 180 and that 3, so we have 5 times 60 from those canceling out. Oops. And then 5 times 60, we get 300 degrees. So a big thing to pay attention to as we kind of work on this chapter is these are helpful and useful, but right here. So whether it's on your calculator, we'll be flopping from degrees to radians and having to make that change. The question might give you something in degrees, but as we're about to see with a few different formulas we have coming up, we have to actually work in radians for it to actually be true. So paying attention to the form they give it in and the form you need to use it in is going to be important going forward, as we're about to see. So our last 4 problems are going to be some applications, and they're actually some pretty good applications, especially if you're going to be doing physics at all. And the key thing on all of these, so I have them kind of all written on the board, we deal with arc length, it has a theta in it, linear speed, which is s over t, but s for us is arc length, so it's just a distance over time, which is typical speed, but our distances are theta, so we have it in 2 forms. So we have arc length and linear speed. They both have thetas. Bottom of that page, you see angular speed with this W. We'll see what that W is. It's going to be a Greek letter. It's got a theta. On that very last page, area of a sector, it's got a theta. In all 4 of these, theta is in radians. So if it's not already given to us in radians, we need to do some converting. So keeping that in mind, we're going to kind of show roughly what is each of these asking, and then we'll go about solving it. So looking at the first for arc length, we have here for arc length, if we have some radius, we kind of swing through some angle to some point. Maybe we'll kind of dot this one too. If we start here, that distance that that tip of that radius swings through, that is our arc length, typically given as S. Now, these sides are always going to be a radius, and that inside angle is our theta. So our radius times our theta, again in radians, will always give us how much the tip of that radius traveled in that arc length. So we look at this problem, we got a circle of radius 4 inches. So we have our R. And the central angle, which is just that angle we swept through, it's given in degrees. We need to make that change first. So first, theta started as 240, but we're going to rewrite it. So again, if we're introducing pi, it's bringing it into radians. 24 and 18, we get 60 going into these. So we get 4 pi over 3. So now we have our theta in radians, and then we're just plugging it in here. So if we have S equals R theta, S is equal to 4 inches times 4 pi over 3. Kind of clean up with those parentheses. So that's going to give us 16 pi over 3, or approximately, here comes our handy dandy calculator, 16 pi divided by 3, we're getting about 16.76. And we want to think about it, 16.76 what, since it's an application? Well, arc length is a distance. So what was our measure for distance? It was inches. So that final answer should be in inches. So that's dealing with arc length. So it's that measure of that arc. Next we have linear speed. So speed or rate is distance over time. But now for us, V will be linear speed. S is going to be arc length because we're traveling through some sweep of an angle. And then we have our theta always in radians. So here's kind of a little graphic for what linear speed is doing. If I kind of have this starting point and I travel some arc, I want to know the very tip of that. As you kind of look straight forward, what is the speed of that, right? So if you were in a car and you're driving, your speed is directly the direction you're going. It's not kind of how much to the left or right you're going. It's always straight on for linear speed. Same thing here. In fact, that would be perpendicular. So graphically, that's what it's looking like. So let's see what we got. We got a second hand on the clock. So do a little sketch of a clock. My second hand, we know the radius. So we already got R. We want to know its linear speed as it passes around the face of a clock. So as this does one full rotation, we want to know the linear speed. Well, if we do one full rotation, we just found out time, right? Time is for seconds to go around. How many seconds? That's 60 seconds. And then we also have our theta kind of straight from that. We have one full rotation, but again, in radians, that's going to give us our 2 pi. So this one gives us a lot of information kind of from that little sketch. So it's going to be R theta divided by time. Our radius was 8 centimeters. Our theta was 2 pi, right? One full rotation on the face of that clock. And then we're dividing this by the 60 seconds. Oh, that's 16 pi divided by 60. And we want to know the approximate speed. Pi is not telling us much. So again, we can crank out that calculator. And we're getting approximately 0.838. And now again, it's an application. We want to know 0.838 what? Well, the speed, so it's some distance per some unit of time. Our distance this time was in centimeters. And our unit of time that we used was the 60 seconds. So again, for this one, we had to make sure that we're keeping things in radians, and the same for the next two. Now, this is linear speed. As we move on to the bottom of that page, we have this weird funky W, which is actually the Greek letter omega, which it's always going to be dealing with anything angular, is this omega. And here's kind of the difference of our angular speed versus our linear speed. So I'm going to draw a very similar picture to right here. So if we kind of swept through that arc, where before we had that linear speed being straight on, our angular speed is measuring more of how many rotations something is doing. So our omega is coming more from this circular path. So linear, straight on. Omega is kind of counting more of the revolutions, not the overall speed. Well, again, it's going to be theta in radians over time. So we give it a read. We have a circular saw with a radius of 4 inches, and it's rotating 2,400 revolutions per minute. So this time is given to us in minutes. So we want to make note of that. Seconds from this one, now dealing with minutes. Well, if we're dealing with angular, it's not bad, right? We just need theta divided by time. We know time because we're talking about 1 minute. Well, we need a little bit more room right here. But we want to think about how many rotations are happening in that 1 minute. Well, we know 2,400 full rotations in that 1 minute. So what is really being rotated 2,400 times? Well, it's our full rotation. So it's making a complete 2 pi rotation, and it's doing that 2,400 times per minute. Well, now we're just going to multiply these out. We get 4,800 pi divided by 1, so 4,800 pi. Get our calculator out, 4,800 pi. Our angular speed is approximately 15,079.64. So now we want to talk about units. So where before we had some linear distance over time, that was that S. This time we're only dealing with how many radians, how much theta we pass through per time. Well, we know our time this time is in minutes. And then those rotations are not just rotations, but there are thetas, which is in radians. So we're passing through a little over 15,000 radians. Again, a radian was that little chunk of that circle per 1 minute. Well, that was for our omega, that's circular speed. Now we want to be able to find linear speed. Well, we got linear speed right here. It's going to be our arc length, which easier for us is the r theta divided by time. Again, we know time. Time is just 1 minute. We know r, it's 4 inches. And then the last thing we know is theta. We just found it before, right? Theta is that 2 pi rotation, and that thing's happening 2,400 times in that 1 minute. That was our 4,800 pi. Well, get out a calculator. We have 4 times 4,800 pi, and we're getting approximately 60,318.58. And now again, we're thinking units. This was linear, so this is traveling some distance for us measured in inches over our unit of time, which is minutes. So lastly, we have area of a sector. That's on your last page. An area of a sector, if I started with my initial side and say I swing through something to this point. That area of a sector, well, what's a sector? A sector is that entire piece you kind of swung through. So it's finding the specific area of all of that. Well, to do that, we have that area is equal to 1/2 radius squared. We'll look at this for this problem. It's talking about the sprinkler spraying 40 feet. So there's our radius right here. Say that that's the sprinkler head right there. It's spraying 40 feet out, and this is rotating through 80 degrees, kind of going back and forth. So we don't quite have theta. To get theta, we need to change that into radian. Well, we got that 80. We introduce pi, so that goes up top. We get 80, so we have in both of these 4, 9, so 4 pi over 9 is now our theta. So we got theta, we got our radius of 40 feet. Now we can plug it all in to get our area of a sector. So you have 1/2 times 40 squared times that 4 pi over 9. Again, anything like this, calculator should absolutely be handy right there next to you. No reason to do this type of stuff by hand. So that's times our 4 pi divided by 9. And I'm getting approximately 1,117.01. And again, we want to interpret what that is. Well, if it's dealing with area, we have area something squared. So what is our distance? It's in feet. So this is going to be feet squared. So again, if we're dealing with any of these four, we gotta have radians. And throughout everything we kind of do from here, the idea of even saying degrees will kind of slowly fade out. So the more comfortable we are with kind of knowing, just get everything into radians, the easier it'll be. But that wraps up our